In our final tutorial, we will convert from rational exponents to radicals and vice versa. So let's flip over to the last part of our notes, and now we're talking about rational exponents. Rational is just another word for fraction. So now we're talking about when we see exponents that are fractions. What are we supposed to do with those? Well, when you see a fractional exponent or a rational exponent, you're representing a radical. You just don't see the radical symbol. So our first step is to be able to convert from rational exponents, the fraction exponent, into radical form. So when you have a base b raised to a fraction like 1 divided by n, this is really the nth root of b. And that's exactly what happens. The denominator of your fraction exponent is the index of your radical. And then, of course, your base is just underneath the radical. If you have a fraction exponent that has a numerator other than 1, so let's just call it m, then there's actually two different versions for this. We could say it's still an nth root. We could say the nth root of and put b raised to the m power underneath the radical sign. Or what we could do is take the nth root of b and raise that entire thing to the mth power, I guess. But it's still the n, the denominator is still the index, and the numerator attaches itself as an exponent to the b or as an exponent to the entire radical, whichever one is easier for you to understand. So the first thing we need to be able to do is convert backward and forward. I take the fraction exponent and convert it into radical form, and you should be able to take from radical form and go backwards into rational exponent. So let's look at 7 to the 1/2. We're talking about a square root. I know it's a square root because n will always be your denominator, and that will be your root, your index. So this is the square root of 7. That's what 7 to the 1/2 power is, the square root of 7. If this is a square root, then the second one must be a cube root. So I know that this is a cube root. And then -8 would just go underneath that cube root. And I want you to work both ways on this one. So let's go backwards. Let's say I give you a 5th root of 10. Could you write that as a rational exponent? Well, the first thing is identify the base, which of course is 10, and then put 5 as the denominator of a fraction. So it would just be 1/5. 10 to the 1/5 is the 5th root of 10. This equal sign works both directions. What if we have multiple things underneath our radical? Well, that's fine. Just take each individual base individually. Take the a. Since it has a 2 attached to it, that must be the numerator, and of course the denominator is 3, the index, so 2/3. And then we'll go to the b. This numerator must be a 5, and the denominator again is still 3, so this must be 5/3. We're just going backward and forward from one form to the other, from radical to rational exponent, from rational exponent to radical. And then, let's look at this one. This one obviously is in rational exponent form because I see some fraction exponents. If I want to put it into a radical, well, what am I supposed to do? They're two different denominators. I want them to have the same denominator. So if I have thirds and fourths, I need to figure out what denominator that has both 3 and 4 in them. So hopefully you're talking about 12. I need x to have some fraction that has a 12 denominator, and the y has to also have the 12. So if 3 has to turn into a 12, I must be multiplying by 4. So if I do that to the denominator, of course I do that to the numerator and make 4/12. 4/12 of course reduces to 1/3, but I need that 12 so that they can both have the 12. Let's talk about this 4. 4 multiplied by 3 gives 12, so we have to also multiply the top by 3 to get 9. So I'm just producing the fractions up. Rather than reducing, I'm producing so that they have the same denominators. And once they have the same denominators, I can write it as, wow, geez, a 12th root. We haven't seen a 12th root yet. They have the same denominators. That's the root, the index, and then x to the 4th will go underneath, and y to the 9th will go underneath. That's a pretty cool problem. What about this one? We've got a square root of 13 and it's being cubed. Well, think about this right here. If we had the square root of 13 being cubed, think about where all those numbers would go right here. Obviously, the 13 is my base, so I'm going to go ahead and write that first. This outer number is the numerator, and the index will always be the denominator. Since I don't see an index, it's implied that it's a 2, so it must be 3 halves. 3 over 2. Excellent. And now our last one. It's very similar to this one, but there's just one little twist in this. Of course, we're going to take each base as itself. So x to the 8/4 and y to the 3/4. Great. Except we're not finished. We always want to reduce. We're not going to leave 8/4 by itself. 8 divided by 4, of course, is 2. So this is really x squared and then y to the 3/4. So this is a new skill. You've just now learned it. It's going to take some practice, but I need you to be able to go from radical form into rational exponent form and vice versa, rational exponent form back into radical form. So we'll have to practice this some more. I'm going to leave you with a try problem. It says write an expression of the form a to the 1 over n that is equal to 5. A can be any real number, and n is any integer greater than 1. So I want you to come up with an expression that is equal to 5. Let me give you an example to help you get started with this. We'll call this example 8, I guess. So let's say I wanted to do the same thing, but instead of equal to 5, let's say I wanted it to be equal to 2. I want a to the 1 over n to be equal to 2. Well, I can just look at my powers table, and I know if I'm talking about something that's supposed to be equal to 2, I know that 2 squared is 4, 2 cubed is 8, 2 to the 14th is 16, 2 to the 4th is 16, 2 to the 5th, and so on and so forth. I know a bunch of things that 2 can be raised to. So I know that I could say 4 to the 1/2 is equal to 2, because this would be the square root of 4. I could say 8 to the 1/3 is equal to 2, because this is the cube root of 8. I could say 16 to the 1/4 is equal to 2, because this would be the fourth root of 16. And I could just keep going up my powers chart from the 4 to the 8 to the 16 to the 32, 32 to the 1/5. This represents the fifth root of 32, and that's equal to 2. I could come up with a bunch of different expressions that fit this form that are equal to 2. So let's call that example 8. Now I'd like for you to do try 1. Come up with an expression that's equal to 5 that fits this criteria, and we'll check this in class. Thanks for trying this. Thanks for watching this tutorial, and we'll see you in class. Please do this try problem and show it to me in class. See ya.